Good morning, everyone. I'm putting this out there for a friend of mine. I wanted to show him a couple things that I've been doing over the past couple of weeks, just messing around. It doesn't have anything to do with Forest fans, so if you're not interested in it, I apologize, but I just wanted to put this out there for him. Basically, like we were talking about, I went back to my code back in the 1980s when I first got into the programming industry, and I grabbed some code off of my Amiga. This is code like from the first shareware applications that I was releasing back then, just before I got started in my career. I was doing image processing. So I have all these old floppy disks from that computer back in the mid 80s to the late 80s mostly. I don't have any of my discs prior to that. So this is all basically from the Amiga computer. And what I did a couple of years ago, and I never got around to using it, I purchased a board called Flux. And what it is, it's a piece of hardware. It costs like $100, I think. And then you got to buy a floppy drive, either a 5 1/4 or a 3.5 inch disc, depending on what you want to work with, and it'll go back and read old Atari discs, Commodore 64, Amiga, what have you. And what it does, it works at the magnetic level, and it streams right off the disk heads using some kind of a flux technology, and it processes the data to try to recover errors. So I went through all my old disks, and I found some of my old source code, and it's pretty cool to go back and look at stuff from 35 years ago. I went ahead and I did that, and then I started getting back interested in it again. Remember, this is from the 1980s. There was no Photoshop or anything like that at the time. So basically, I learned how to do a lot of image processing, and back then, and eventually that's what led to my job. So anyhow, I just wanted to show you. Yeah, this is the app. It's called Flux, and it comes with hardware. It works over the USB port, like I said, and it'll go through. I was copying both sides of a high density disk here on the Amiga, and it recovered everything into ADF files, which of course means I can run it in the emulator. And I use an emulator called WinUAE, WinUAE, and allows me to fire up an old Amiga 1000, 2000, 3000, 4000, 1200, whatever model, and it'll read these. You can see they're 880K each. So I got all my code on here, and then I went on the Amiga, and then I copied it all over to the PC, and then of course I'm just messing around porting some of that code over to Windows. You can see I got some of it back here. This is just Floyd-Steinberg dithering, and I'm going to show you that. That's actually what I'm making this video for. So yeah, that was pretty cool. It worked out really well. Anyway, I just wanted to show you the results. And a lot of this code, like I said, came from many years ago, minimum of like 20 something years back, all the way up to approximately 30, 32, 33 years ago. So here's the results of one of the image. This image here, this is the original. It's a BMP file because I converted it, but it originally came from a JPEG. It's got roughly 198,000 unique colors in it. What I did is I was messing around. Now, back in the day, I was using an algorithm called the median cut, and frankly, I think it's better than this algorithm. Right here, I used the Octree Quantization. So I use an Octree and I convert it down from 198,000 colors to 256 colors. So this is the optimal palette basically that you would get to represent this image. Now, obviously, when you quantize an image down from 198,000 to 256 colors, you're going to end up with the banding like we talked about. You can see it all back here, but this is basically an optimal palette. So what I did is I implemented Floyd-Steinberg dithering. This image here is the dithered version of this image. So this has 256 colors in it too, but you can notice the detail is much better. And compare it to the original that has 198,000 colors. This one has 256, and it's dithered using Floyd-Steinberg. You can see the dithering pattern back there, but there's nothing you can really do about that. It certainly looks a lot better than just using the quantized image. Yeah, I'm messing around with that. To go from here to here, and my code isn't optimized yet, but it takes roughly little bit, about a second, and that includes the loading and saving times of the image. I could load the original image, quantize it, and then I can dither it using Floyd-Steinberg and then save it, and all of that takes roughly about a second on the PC. Of course, it's slower on the Amiga, but and Amiga has other issues too related to the amount of memory. But I haven't really optimized the code. I don't really know if I'm going to. But yeah, we talked about how the Octree works, and you understand that now. But the median cut algorithm, right off the bat, it reduces the colors down from a possible 16,777,000 down to roughly 65,000 colors, and then it puts them into a three-dimensional cube, and then it divides that cube up into subcubes recursively, and then it takes the median of the colors that are in that cube, and then it basically subdivides the cube again recursively. And eventually you end up with 256 cubes. That's your palette. And then you go and you average all the colors out in all the cubes, and there you go. But one of the changes that I made to the median cut that really improves it, instead of slicing the cube right at the median point, what you do is you find the channel that has the longest leg. So if there's like more variety of red, that will be the red channel will be the widest. If the green has more variety, then it would be the green, and so on. So you find the longest leg. Of course, you find the median point, but instead of splitting it at the median point, what you do is you search forward and backward and make sure that you're splitting it between shades of the color with the longest leg. And it makes a difference because otherwise you end up with duplicates in two different cubes and it kind of wastes space. So you might be able to squeeze an extra couple of colors out of that. But that runs real fast. It runs in real time. And we were using it in the ray tracer when I worked at Impulse back in the 90s. And the reason why we were using it is because when you're in a 3D program and you're tweaking the parameters for, let's say, a texture, you want to be able to do it in real time and see the results. You want to be able to drag the sliders around and get updates in real time. And the problem is that we're dealing with images that can have 16 million colors. So we got to reduce it down to 256 back in the day because the VGA monitors and stuff on the PC or even the Amiga only displayed 4,096 colors, and the PC was at 256 colors. So in order to see it in real time, we had to do something really fast. And the Octree can get better quality, but it doesn't work in real time. And it also consumes a tremendous amount of memory because, like this image here, with 198,000 colors, you end up at roughly a little over 300,000 nodes. And each node takes up roughly 50 bytes. So you're talking about 10 megabytes of memory just to manage the Octree to go from this to this. Whereas the other method with the median cut, since it goes down to 65,535, you could fit that into 16 bits. So it immediately chops the memory in half, right? So now you're down to actually a little bit less than 5 megabytes instead of 10 megabytes. And that algorithm, like I said, it works in real time. It's extremely fast. And in my opinion, if I did the median cut one over here, you would, even without dithering, it would look better than this. And that's the other interesting thing about median cut. Median cut produces better results, even, like I said, without the dithering. Ultimately, though, depending on how low you want to go, because I could take this from, 16 million colors down to 16 colors. 16 colors, you're only going to get so good. But actually, 64, or if I went down to 128 instead of 256, it would actually look, you really wouldn't be able to tell the difference that much, except in certain areas where it's shading. But you would definitely notice it if you didn't have the dithering. So anyway, that's all I wanted to show you. That's what I was talking about the other night when we were on the phone. So yeah, you might want to go back and look for some of your old code. It's interesting to go back, 35 years in time and look at what I was doing back then and compare it to what I'm capable of doing now. Obviously, I wished I knew what I knew now back in that day. So yeah, this is just messing around right now. But I'm gonna try to use this for something commercial that I'm working on. So I'll go ahead and improve the algorithm, speed it up, make it take less memory, clean things up. But I just wanted to show you this really quick. So cool stuff, man. Hopefully I'll talk to you during the week. Peace.